It's a good plan. All right, sound check, check, check. Is anybody out there? Raise your hand if you can hear me. Perfect. All right, going live. First time I've done a live lecture in many weeks. It's going to be good to be back on campus, let me tell you what. I'm ready to do my job. All right, I think I got all my screens in order here. I can see what I need to see. I can just see chats on the side there. I think somebody's going to be managing this. I'm going to let that happen. So, hold on a second. I feel like there's sound pressure coming. Closing that up so we can go for it. All right, so this is lecture 19, graphs and graph algorithms. We're talking about graphs today. We'll start out with looking at how we define graphs. This is pretty straightforward. We've already had some graph experience this semester, and we've seen trees as well. And one of the things that's important to remember is that all trees are graphs, just not all graphs are trees. Here's our formal definition. We've got this graph G, which is a combination of these sets V and E, where V is a set of vertices or vertexes. Either one of those is correct, and for some reason I shift back and forth between them without any real rhyme or reason. So sometimes I'll call them vertexes or sometimes I'll call them vertices, but both is correct. So there's a set of vertices, there's also a set of edges. It's also common to think of vertices as being called nodes. That's also correct as well. So all of those kind of tell you how we look at this graph. It's a collection of places and a collection of connections between those places. We often represent our edges as ordered pairs. We can see that here where we've got E sub m as this set of vertices, V sub s, comma, V sub t, and that represents an edge between these 2 points, S and T. Quick quiz, and I already gave this one away. My intro slide, I talked about all trees being graphs. That's definitely a tree. In that case, it's definitely a graph. So I've got what I mentioned earlier. I said that my graph is a collection of vertices. Those are my numbers, those little bubbles with numbers in them, and it's a collection of edges that connect those vertices, and we can see those lines that connect each one of my edges here. So yes, this tree is actually also a graph. How about this? Is this a graph? Well, I certainly have vertices. Those white bubbles actually didn't change. My edges, however, have changed quite a bit. I see I got a little group down there, that 54, 88. They're not connected to anything. 48 has this weird edge that leaves 48 and returns to 48. And then the distance between 17 and 50 is actually covered by two different edges. But if you listen to the way that I described all of this, I didn't make anything new. I said I had vertices and I talked about edges. And so this is a collection of vertices and edges. So yes, then this is a graph. It has what we call a self loop there. That's from 48 back to 48. And then we also have parallel edges. They're called parallel. They don't have to be physically parallel, but the fact that there's two edges that run between 17 and 50 make those parallel edges. And then of course, I know that trees have to be connected. There can be no isolated points in a tree, but that's not true for graphs. So I can have 54 and 88 all by themselves and still be considered part of this graph. It's just that there's no way to travel from edges to 54, from 54 to 44, for instance. And that's okay. One of the things we can think of oftentimes as supporting graphs is road systems. So imagine if you've ever traveled around Michigan, those of you who aren't from Michigan, we have a couple of really large islands, Mackinac Island, Beaver Island, and there's one down in Detroit area, Boblo Island. There's Belle Isle. There's a few islands here, and some of those islands have roads on them. So if you're dealing with the road system in the state of Michigan, you can say that there's roads throughout the continental portion of Michigan. But then there's also roads that exist on our islands. It doesn't make them less roads, and it doesn't make the places that they connect less places. So we have the ability to have disconnected sections in graphs that we don't support in trees. So yes, this is a graph. In more detail, we could say that in general, we do allow parallel edges. The general definition of graphs allows for parallel edges and self-loops, but most of the time in 281, and most of the time in general, you're generally talking about what we call simple graphs. And simple graphs don't have parallel edges and they don't have self-loops. So if we don't mention it, we're generally talking simple graphs, and you can imagine that parallel edges and self-loops will not exist. So unless it's explicitly specified that this is not a simple graph, assume simple graphs. So now we see this is another graph, to be sure, but it's definitely not a simple graph. And it's not simple because of the self-loop there, not because of the disconnected section. That's fine even in a simple graph, but what makes this not simple is that self-loop. So yes, that's a simple graph. Here's some more definitions as we start talking about graphs. A simple path is one that's just a sequence of edges that goes from one vertex to a next with no vertex that's being doubled. So a simple path goes from point A to point B with however many intermediate points there may be, but none of those intermediate points are visited more than once. A connected graph is one where a simple path exists between any pair of vertices. So if I can get from any vertex to any other vertex, I say that I've got a connected graph. And that's just a fancy way to say that there's no islands. Okay. Cycle is of course a simple path because we don't have doubles in there, but it starts at home, makes a travel, and comes back to home. So we say that a cycle is a simple path, but it does allow for the first node and the final node to be the same. So there can be one duplication in a cycle, but it has to be the beginning and end of the cycle. As we look through graphs, we're going to find quite a few different ways to categorize them. The next one talks about directed versus undirected. A directed graph, which often gets called a digraph, it's an easy way to short that up. It's the DI from directed and then just graph from graph. So a digraph is one where the edges have directionality associated with them. So if you've been to a downtown area, you'll know that there's one-way streets quite often in downtown areas. Those are directed edges. You can only go from A to B and not the other way around. right? So in this case, I can say that my nodes that I use in my edges, where I've got this pair v sub s comma v sub t, or in this case I've got e sub n goes from u to v. This means in a digraph, in a directed graph, that the edge goes from u to v and not necessarily in the other direction. That's actually a separate edge. If I wanted an edge to go the other direction, I would have to have something going from v to u. Now, we don't think of parallel edges in a digraph unless they're both going the same direction. So if I've got sort of a connection from A to B in a digraph, and I've also got a connection from B to A, those aren't parallel edges because one travels this way and one travels that way. They're not parallel because they're different directions. Now, if I've got two ways to get from A to B, these are parallel edges because they're going the same direction. In an undirected graph, I don't really care about the order of the vertices in my pair. So I can think of them as unordered pair. I can think that this E sub n, which has U and V in there, just means that there is an edge between U and V, not necessarily that it runs from U to V. It's between there, so it can be used from U to V, and it can also be used from V to U. So there's one way that we distinguish graphs. We talked about digraphs and undirected graphs. Here's a quick way of how this might look visually. You see that I've got the same undirected graph with my edges having no arrows, whereas the digraph on the far side, there are arrows there that point the direction of travel. So I can go from 2 to 5. I cannot go from 5 to anywhere, right? So this means that I've got this directed graph here, and you can see those arrowheads tell me the direction of travel. Another way that we categorize graphs is whether or not we have weighted graphs. We call them weighted or unweighted. In a weighted graph, I've got these edges that hold additional information. Most of the time when we talk about it, we keep one piece of information for that weight, but we talked earlier in the discussion, and if we wanted to, we could associate more information with one particular edge. But for the algorithms that we're going to be dealing with in 281, it's about that weight. And you can think of the weight as being the distance between two nodes, or maybe it's the cost to travel between two nodes, or the time it would take to travel between two nodes, or the amount of money you would spend building the road between point A and point B. That's totally determined by your problem definition, but the weightedness of a graph talks about associating some resource cost with an edge. If I've got undirected graphs, I can have parallel edges. Remember, we said we can have parallel edges, and it's possible to have multiple parallel edges with different weights. And how you might think of this is, how many different ways do I travel to get to work? I start at home, I end up at work. There's my two nodes, but what about the edge that connects them? Do I take the highway? Do I take the surface roads? It's the same two vertices, but different paths, and as such, I might have a different weight associated with parallel edges. Because I can say if I take the highway, I can get there in this amount of time, but if I take the surface roads, I'm going to get there in that amount of time. Or the highway trip is longer and the surface roads is shorter. So it's possible to have, in undirected graphs, these weights that are different for parallel edges. When we start adding weights, though, now we've got the ability to do something where we compare. Without weights, an unweighted graph, all we can really check is connectivity. Is A connected to B? Is it connected directly? Is there an indirect way to get from A to B? Whatever, that's the kind of thing that we look at. So we're often looking for a path just to see if it exists when we're talking about unweighted graphs. But when we start assigning weights to these edges, now we can start optimizing. Say, well, what is going to be the least cost path? How can I get from A to B with the least amount of resources spent by traveling on the edges that use the least amount of them? So we can start taking and optimizing things once we've got weighted graphs. All right, what do you think about this one here? We already talked about directed and undirected. Is this a digraph? We talked about weighted or unweighted. What do you think? It looks like I don't see any arrows. So right away, I'm going to say this is an undirected graph. And we didn't really talk about how it's displayed, but you can see how those numbers that are floating over the edges there are associating some value with that edge. In this case, we're looking at some set of flights in the US, and those are the miles that connect them. 2,704 miles from San Francisco Airport, that's SFO, over to Boston Airport, that's BOS. The other airports in there, in case you're unfamiliar, there's Los Angeles, LAX, Dallas, Fort Worth down in the middle. On the far and the bottom is Miami. And then across the middle of the country there, we see Chicago O'Hare, which is ORD, and New York City, which is JFK. So this is an undirected weighted graph. And we're going to use this one through our next set of examples. So let's get a little bit familiar with it. All right, that's how we look at graphs. We've looked at their high-level mathematical definition, G, V, and E. Excellent. Here is another look at the United States. Those of you who are fans of board games may know this game. It's called Ticket to Ride. It's a game about trains. So if you're a fan of TV shows that talk about trains, Sheldon would really dig this game. So here you can see that our graph, which is these circles, those are my vertexes, and then these little rectangular segmented lines, those are my edges. That's superimposed over the United States. And that's often what we use graphs for, is we use them to sort of focus our attention. Obviously, there's many other locations in the United States than just this handful that's represented here. And there's also many other paths. But we can use graphs to abstract what's important about this. So this particular version of it's talking about train travel, and you can see how the number of segments between each one of my vertices, that's the cost of the path. So you can see some 5 cost paths here. Across the middle, you can see some 3s and 4s. There's a 2 and even a 1 down there between Dallas and Houston. But this is a great way to see how graphs help us abstract away some of the things that we don't care about, so we can really focus on the travel that we do care about. Now let's talk about how we're going to implement graphs in code. Some of the ways that we look at doing this. When I look at the data structures that I'm going to use, I've got to know how many of these things do I even have to look at. If I've got a complete graph, and we're still talking simple graph, right? A simple graph doesn't have parallel edges, but I can say all possible edges in a complete graph means that every vertex is directly connected to every other vertex. That ends up with talking about this absolute value here, and so we see the absolute value bars that are placed on this E really refer to the magnitude of set E. So we'll get a little bit lazier later, and we'll just be talking about E and V as if they were numbers. But E and V are not numbers. E and V are sets. So when I put these vertical bars on there, I'm saying, tell me the magnitude of set E, which is really how many items are there? How many edges are there? So I say the number of edges is equal to the number of vertices times the number of vertices minus 1 divided by 2. That's all the possible edges, right? And that ends up to be something that looks like approximately V squared. If you're getting really particular about it, it's V squared minus V over 2. But that still ends up in big O terms as big O of V squared. So a complete graph with all possible edges has approximately V squared edges. New definition here. We were talking about weighted, unweighted, directed, undirected. Now we're going to talk about dense versus sparse. So in a dense graph, I think that there's many edges. In this case, the number of edges is on the order of the number of vertices squared. So that's what this little thing represents here. I say E is approximately V squared. So this is kind of a loose definition, but you can think of, if I add a bunch more points, how many more edges do I add? So if I've got a dense graph, I've got 100 points, and I add 5 more points. Each one of those 5 points needs to have approximately 100 more edges coming out of it, because it needs to be connected to most of the other things. That's what dense is. It's loose. We don't have a real tight grasp on it, but we do know that the opposite of that, sparse, says that we've got approximately E equal to V edges. In this case, the magnitude of V, magnitude of V. So I'm looking at having about the same number of vertices and the same number of edges. When that's the case, I've got a sparse graph. Or even if I've got a constant number of edges per vertex, I would say that that is a sparse graph. So if each position is connected to just one other position or 2 or 3 other positions, that's a sparse graph. So this is, to be honest, a small example of this. It's hard to really grasp it with just 5 of them. But you can see that this complete graph here shows every one of those 5 items is connected to every one of the other 5 items. So each one of those positions has 4 edges leaving it. Each vertex has 4 edges connecting it to other vertices. That's a complete graph because there's only 4 other vertices per every other vertex. And that's how we get that calculation. We said it was V times V minus 1. So for every one of these vertexes in the V set, there's all of the rest of them, V minus 1, that it has to be connected with. But rather than counting the edge from 1 to 3 and the edge from 3 to 1, it's just the same edge, I divide that by 2. So I've got V times V minus 1 divided by 2. And this is the same thing. You say, well, I just walked into a party. There's 10 people that don't know each other. We all have to shake hands. How many handshakes are there? There's going to be 10 people. Each one of those 10 people needs to shake hands with 9 other people. So that looks like 90 handshakes. But if you take into account that me shaking hand with her is the same as her shaking hands with me, we don't have to do that twice. So we take that 10 times 9, divide by 2, and we get that total number of handshakes there. In the middle, we've got another dense graph here. And like I said, this one's a little bit harder to see, but there's quite a few more connections there than the one on the far side there, where you see that sparse graph. On the sparse graph, each one of those is connected to about 1 or 2 of them. 4 is connected to 3, but most of them are not connected to very many. So that's a sparse graph. In the middle is dense, and then this one here is complete. A complete graph is where every node is connected to every other node. How about this? Complete, dense, or sparse? What does complete mean? Every node is connected to every other node. I can clearly see that 17 is only connected to 44. So complete, out. What about sparse or dense? Here, I've got each node connected to, at most, 3 other nodes. You see 50 is busy there in the middle, so is 62. They've both got 3 node connections. But 78, 88, the rest of them are only connected to 1 or 2. So I would say that this is not complete and this is not dense. It's sparse. Okay, representation time. How do I keep track of the edges that do exist? Down there, you see the picture that we've already looked at. It's this picture of the United States, and it's got some airline routes superimposed over the top of it. Great. Pictorially, I get it. How do I represent this, however, in code? One way to do it is with what's known as an adjacency matrix. And we see this adjacency matrix here. We see each one of my locations has its own row, and each one of these locations has its own column. If I put them together in this 2-dimensional thing, I can see what's adjacent to what by looking from a row and then traveling over to a particular column. So I don't worry about self-loops. So you can see that diagonal that goes from top left to lower right, that's going to be a bunch of zeros because we don't want to talk about San Francisco being connected to San Francisco. San Francisco is connected to Los Angeles though, and that's what I see in that top row, second number from the left. LAX is connected. So here I've represented just the fact that these things are adjacent by putting a 1 in there, right? And adjacent in terms of graphs means not physically how close they are, but whether or not there's an edge between them. Because you can see that San Francisco and Boston are nowhere near each other. But in terms of graph speak, they're adjacent because there's an edge that connects them. So if I start in the SFO row here and travel all the way over to the Boston column, you'll see that there's a 1 and that they are connected. So this adjacency matrix here is a way to represent connectivity. I can do a constant time lookup for any particular starting location on this vertical set of rows, and then move over to my horizontal set of columns and travel down that and see if there's an intersection. And sure enough, you can see that JFK here is not connected to Dallas-Fort Worth. So I move over to that third column, DFW, and there's a 0 there. If I look down on my map, I see that DFW not connected to JFK. But if I move over one more, JFK is connected to Chicago, and you can see that 740 link across there. So the weights are in the map here, but this matrix just represents adjacency. So I don't have weights there, I just have whether or not they're connected at all. So the connection between JFK and ORD is represented. I can find that by going to the ORD row and checking the JFK column, or I can find it by going to the JFK row and checking the ORD column. In this case, because I've got an undirected graph, you'll see that it's symmetric across that diagonal there. ORD to SFO is represented, so is SFO to ORD. So we think of this as the froms and across the top as the twos. So this is an adjacency matrix. Here then is a distance matrix, which should follow pretty directly. You can see that I now have the weights involved in my matrix. So I can say, well, what's the distance between Chicago and New York City? I go to the ORD start, I travel all the way over to the JFK column and see that the distance there is 740 miles. So this is what a distance matrix can do for you. And places that aren't connected here, I've represented them with zeros. The next way that we talk about a high-level graph representation is by what's known as an adjacency list. This one has kind of got more of a linked list feel to it. And what I've got is a collection of starting locations. That's what those orange boxes are. You can see them, SFO, LAX, DFW. And then they point to all of the vertices they are adjacent to. So this is not a linked list in the sense that LAX points to DFW. Look in that first row. I see SFO points to LAX, LAX points to DFW, DFW points to ORD, ORD points to Boston. That does not mean that there is necessarily a path from LAX to DFW. What I'm trying to represent here with this adjacency list is from my starting location in the orange box, SFO, I have definite connections to all of the things in this list. So SFO is connected to LAX, SFO is connected to DFW, SFO is connected to Chicago, SFO is connected to Boston. That's what's going on in that top row there. It turns out that Los Angeles is actually connected to DFW, but I don't find that until I get to the second row here that starts at LAX with the orange box, and then if I go look through the list, I look through the adjacency list, these are all the things that are adjacent to LAX. So since DFW is in that second list, then DFW is adjacent to LAX, right? It's not adjacency between LAX and DFW is not in the first row, it's only in the second row. Down at the bottom it says, note here, adjacency list nodes can contain distances. So you can build this just like a linked list. If I've got a node that's got a pointer to next, for instance, and I can stick a bunch of things in there, but you just have to worry about how it's, or what it means semantically. Just because things are connected in this list doesn't mean that they're connected to each other. It just means that they're connected to SFO. And just like in a linked list, I've got room for data. If I wanted to, I can put distances in my adjacency nodes, adjacency list nodes. So I can represent those edges. And so you would see here in the first blue box there, the SFO that points to LAX. If I went to the map down there and saw what's the distance between SFO and LAX, it's 337. I could put 337 in that blue LAX box. And then what would go in the SFO to DFW box, in that second blue box on the top row, I would put that 1464 from the map. It shows that SFO goes to DFW in 1464 miles. That's completely different from what I would put in the DFW box on the next row. Right? The DFW box on the next row is being pointed at by LAX. So the DFW box in the second row, the blue one there, should have 1235 in it because the distance between LAX and DFW is different than the distance between SFO and DFW. So this is an adjacency list. It allows us to both represent adjacency, connectivity in graph speak, what items are connected to what items, what vertices actually have paths to other vertices. And if we want to assign some additional information in there, we can also get weights as well. All right, adjacency matrix, let's dig in a little bit deeper. As I look at this V by V matrix that's representing the graph, I can see that I've got this V squared memory tied up there. If I've got a directed graph, then I start with my froms in this left column and my twos on the top row. And so I'll start from here and go to there, and that's where I'll find one of those edges in a directed one. So in this case, I can see that there's from and to. However, in an undirected adjacency matrix, I could actually just eliminate half of that triangle if it really mattered to me, because in the undirected matrix, we know that it's symmetric across that diagonal. So I don't need to represent the full square. So in that case, I could save some of my memory, half of it, V squared over 2 space. Still obviously using big O V squared space. So you have to monitor what your savings get, because now if you use an undirected adjacency matrix, then you always have to, an undirected adjacency matrix that's half populated, I would have to make sure that I always access them in the right order. So you can do that. In the unweighted versus weighted, obviously with the adjacency matrix, I can say that no edge means 0 when I'm unweighted, and a 1 means there's connectivity, adjacency. That's what I do. That's what I showed with that first adjacency matrix. But then look at this one down here. I say for the weighted one, I should say that the no edge would be represented as infinity. If you remember that early picture, the first picture of my distance matrix, I had the weights in the graphs, but things that weren't connected, I said that there was a 0 edge between them. Looked great for the humans. It's not so good for the computers. Why? Because usually as I'm trying to sort of minimize a distance, I say, what's the distance between here and there? It's 337 miles. Great. What's the distance between here and there? It's 0. Oh, I'd rather take that 0. Wait, 0 represents no connectivity? Well, that's not great, because I want to just do something simple and say, if this is less than that, use this. So a better way to represent no edge in a weighted distance matrix is to use infinity. Because then I can say, which would I choose? The 337 mile path or the infinity path? I'll take 337, thanks. So here is an updated distance matrix. You see now I've got those infinities in there, and you can see why I would never try to choose to go from Miami directly to San Francisco, because it would be infinity to get there. So you can also see that this is undirected now. You see that line of symmetry across my diagonal there. I've got LAX to SFO as the same distance from SFO to LAX. This is an undirected distance matrix. As we've brought up infinity, let's make sure we get this done well in code. You include limits, and then we can call for this infinity here. And we only need to worry about infinity when we're talking about our floating point types. So our floating point types give us this concept of infinity. Because remember, infinity is not a number. Infinity is a concept. So you don't want to do math with concepts. You want to do math with numbers. So if you've got an infinity, you can use it for comparison. It's bigger than anything you can find. But you can't add it. You can't add infinity plus 1 and expect to get something reasonable from a computer. So don't do math with infinities. Not the least of which reasons not to do this is because different platforms implement it differently. So if you multiply 0 by infinity, for instance, in Visual Studio, you'll get 0, or you'll get not a number in G++, because you shouldn't do math with infinity. So be aware that you should use infinity when you're really trying to represent something large, something that you can't reach. Don't use max. It's not quite the same. Infinity is actually larger than max. Max just represents the largest value that I can represent in a floating point number, whereas infinity represents the largest concept there is for numbers. All right, we've talked about adjacency matrix. Now let's go back and talk about this adjacency list. Here's the tough one to get. How many edges connect to each vertex? We don't know from a general standpoint. Obviously, if we're talking about a specific graph, yes, we know. But in the general case, how would you describe how many edges come off of each vertex? One way to do it is to just take a simple numeric average. Think there's 50 edges in a graph and there's 10 vertices. I could just divide the number of edges by the number of vertices and say, with 50 edges and 10 vertices, on average, it sounds like there's about 5 edges per vertex. That's what this approximate E over V is. So I'm going to use the adjacency matrix and the adjacency list in two different situations. I want to use the adjacency matrix when I've got a dense graph. Remember, the adjacency matrix is costing me this V squared. If I'm expecting to have most things connected, then I'm going to have about V squared edges. However, I don't want to spend a lot of space if I've got a sparse graph. That's where adjacency lists come in, because then I can say, well, this node is only connected to 2 other nodes, and all I have is 2 items in its list. If there's, say, 40,000 nodes, I don't have 39,998 blank spaces here, because with the adjacency list, I only connect each vertex to exactly the vertices that it's actually connected to. So the adjacency, if you wonder why there's the both of them, the adjacency matrix is good for representing dense graphs, and the adjacency list is good for representing sparse graphs. So as I think of this small number of edges in a sparse graph, I can say that there's approximately E over V edges on each one of these vertex lists. So now, as I try to figure out, is there connectivity between A and B, what does it cost me to get there? Well, first I've got to access the start position. I can get there in constant time, let's say the big O of 1 there, to get to the head of that list. And then I may have to look at as many as E over V items in there. And that's my average case. Obviously, there's best case where I find it in one look, and there's worst case where one particular node is maybe like a wagon wheel, where it's connected to every other vertex. And so then to find out connectivity, I might have to search all of the other ones. So the average case, however, though, says that in that vertex list from an adjacency list, there's about E over V other vertices that it's connected to. So there's E over V edges that I have to actually investigate to see if this starting vertex is connected to a particular vertex. So if I say that checking out one individual vertex means getting to its start and then finding it in that list, I'll say that's a big O of 1 plus E over V, because I can access the start in constant time. You can look that up as some index in an array, or if you wanted to, you could say, I'm going to put all of these starts in my adjacency list in an unordered map. Doesn't matter. You can get there in constant time. Then you've got this small linear search. And we're hoping that it's small because we don't want to have to search all the vertices. We'd like to search some subset of them, and that's where this E over V is helpful when we've got these adjacencies. So I'm going to say the average cost for managing one vertex is this 1 plus E over V. And that looks bad because we've got 1 plus inside one of our big O notations. And normally when we're talking about big O, we just cancel any of this silly math. So I'm going to leave it as 1 plus E over B because that's the cost of one vertex. And then if I want to process the entire graph, which is usually what you do with graphs, you generally process the majority of the graph, if not all of it. So if I say one vertex costs me 1 plus E over V, and I have to process all V vertices, then I can multiply that 1 plus E over V times V. And you see that here in this bottom line, where I say that V times big O of 1 plus E over V is actually big O of V plus E. And that's what it feels like to process all the vertices in an adjacency list. You're doing on the order of V plus E work. Now, if I was to simplify this big O expression like I would like, if I wanted to just call this, well, it's really just big O of E over V, then when I multiplied that by V, I would feel like the cost for doing all of the work is just E. And that's not quite right. The number of vertices in there also matters as well. So that's why we keep that 1 around. It's just for this particular usage of the way that we talk about big O's. All right, adjacency list. When we talk about directed, undirected, weighted, unweighted, that's pretty easy to figure out. In my directed versus undirected, you know that I can start at the head of my list, and then everything in the list are the things it's connected to. So it's pretty easy to see directed there. I start at my source, and those are the things that it points to. Now, to figure out if something points back to this, I have to go to its start and check to see if it's in there as well. So in my directed graph, each edge is in there just once because it starts here and goes to there. In my undirected graph, I can say that these adjacency list has to have both of those things in there because I need to get from point A to point B, and then I need to get from point B to point A. So each edge shows up twice in an adjacency list when it's undirected. When I'm talking weighted versus unweighted, this one is pretty straightforward as well. When I've got a no edge, there's no connectivity, that's great. I don't have to do anything. By default, adjacency lists represent no connectivity really well because you don't put anything there, it's not connected. So if there's no edge, it's not connected. If some vertex is not in another's vertex's list, they're not connected. If I do have something in there, then there's my edge. If I want to put some value into that, I can also include the weight just as easily. I can say the list item with a value now says that there is connectivity and this is how much it costs. No edge, of course, either way, weighted or unweighted, is simply represented by having nothing. So this question comes up enough to get its own slide. See, I kind of breezed by the fact that how do you get to this constant time access of these orange items here? Well, here you can see the entire map all set up with this adjacency list. How do I get to San Francisco? Well, I could put this in an unordered map. If I was going to be using city keys and someone was typing in SFO to their computer, I could put in my unordered map when the key is SFO, give me this list. That's one way to do it. Or I could do a translation and say, well, someone asks me for city at index 3, so I go 0, 1, 2, 3, or you're talking about Chicago. So if this is a sort of vector of orange things, I can get to any one of them in constant time with random access. If this collection of orange things is, this collection of list heads is an unordered map, I can also get there in constant time. So you can get to these list heads in constant time. That's no problem there. And there you can see here that I've got some average number of things per each one of these things, and this is what I've got for my adjacency list. All right, that's graph implementations. We had two primary ones that we looked at. We talked about adjacency matrix. We use the adjacency matrix when we've got a dense graph and we've got a lot of edges. The number of edges is on the order of v squared because I'm going to use v squared memory in the adjacency matrix. I want to have that worth something. So if I'm going to use v squared memory to represent v edges, I'm probably doing something unnecessary. This is where the adjacency list comes in, because now I can just represent the edges that I actually have, and I don't have to represent the possibility of edges which may or may not show up. So one of the things that we talk about here in terms of examples of sparse versus dense. Let's go to New York City. If you've been to New York City, raise your hand. Live lectures, it's fun times. New York City, big city. Lots of places. Let's say that we're going to take the street map of New York City and represent each intersection as a vertex. And then all of the roads that connect these intersections, those are my edges. What would you think of New York City represented this way? Is that a sparse graph? Is that a dense graph? Is that a complete graph? Well, complete sounds absolutely ridiculous, because that would mean that every corner in New York was directly connected to every other corner in New York by one street. So complete is out. Is it sparse or is it dense? There's a lot of streets, there's a lot of corners, there's a lot of people. It's New York City. But if you pause and think about each one of those intersections, kind of like this. Right there in the middle of that, you can see that it's only really connected to one street to the north, one street to the south, one street to the east and west. So each one of my intersections, as many of them as there are, still only has some constant upper limit to the number of items that they're connected to. And it's on the order of 4 in this case. So I would say that representing New York City as a graph would be best using sparse graph methods, because most intersections are not connected to most other intersections, right? If you pick some number, I have no idea what it is. I'm not even close in magnitude. Say there's 10,000 intersections in New York City. Most of them are only connected to 4 other places. So if I had a row that allowed me to have 10,000 other places, that would be wasted memory, because at most 4 of them would be used. Now there's some strange intersections. Some have 2, some have 3, some have 5, 6, but most of them don't have hundreds of other connections. None of them do. So that's how we might look at graph implementation. The third way that we didn't even talk about comes to us from Project 1. We did Project 1, we've got this 2D representation of a map, and how do we get from one to the next? We used a formula. We said, well, you can travel one space to the north, one space to the east, one space to the west. So just like New York City, we had this graph. So Project 1 was a graph search. We did a graph search, but we came up with a real rules-based way to represent that graph. We didn't have to explicitly represent each edge. We had a way to calculate where edges existed. All right, we're going to move on into some talk about algorithms here. Some of our simple algorithms, and we'll be talking more in the future about more graph algorithms. It's going to get us an introduction to it. Of course, we're going to be talking about complexity. We've got to deal with edges or vertices. The number of edges, which we'll simply call E, or the magnitude of E. The number of vertices, magnitude of V. Or in some cases, as we saw that processing all of the nodes in an adjacency list was going to cost me a combination of these two. We call that big O of E plus V. So as we look at complexity, it's important to understand what our algorithm is doing and how our graph and the algorithm are going to work together, because sometimes our N is actually E, sometimes our N is V, sometimes it's a combination of the two. So let's start out with some simple algorithm questions. We'll do some design work here. Up top, I've got the question, and what I want is the worst, best, and average when I get these things. Down here, I've got the adjacency matrix version of it and the adjacency list version of it, just for viewing purposes. So the first question is, determine whether a nonstop flight from X to Y exists. So given two cities and my two representation types, let's figure out the worst, best, and average complexity for both representations. So let's start with the adjacency matrix. To determine whether a nonstop flight from X to Y exists, I kind of go down the column here to find the X. I go across that row to find the Y. I can look in there and figure out whether it exists. So it looks like I can get there in constant time, right? Best case, worst case, average case. That's whether a nonstop flight exists. How about the adjacency list? Well, I can get to the base here in constant time, say SFO in constant time. Now if I want to know if SFO to JFK exists, what do I have to do? I have to search this adjacency list. So I would say that in the best case, I've got an empty list, and I know they're not connected. Or another non-trivial best case is if I'm looking to see whether or not San Francisco to Los Angeles is a connection. I look in SFO and LAX is right there. So best case, I can say I can check that out pretty quickly, constant time there. Worst case, I look through the entire adjacency list to find what I had to find. Or I look through the entire adjacency list to find out what I'm looking for isn't there because they're not connected. So in that case, then my worst case is the length of the list. How long can the list be? Well, it could be empty, that's my best case. It could actually be the wagon wheel hub. So one city is connected to all the other cities. So in that case, I've got to search the entire list. I have to search all n-1 of the other cities. So, or v-1. So my worst case there then is going to be something that's big O of v. But my average case is going to say that, oh, they're roughly distributed evenly. So I'm looking at E over v there. So we can see here as I pump through the answers, worst case is constant time, best case constant time, average case somewhere in the middle there, that's constant time. On the adjacency list, I've got the worst case is all of the items are in this SFO list and I have to look through all of them to find it. So that's big O of V. My best case is it's either empty or I find the thing I'm looking for in one pick, constant time. My average case is this really strange one that we already discussed. This big O of 1 plus E over V. Constant time to access the orange list head, and then average lookup of E over V vertices connected to the list head. All right, talking. Let's do another one. New task, same setup. What is the closest other airport starting at X? So given any particular location, how do I find the closest airport starting there? Let's start with the adjacency matrix. How do I find it? Well, in the broad scope, I've got to look at all the things in that row. And I can't look at one of them and say, well, that's the shortest. I know it's the shortest. I found one. It must be the shortest. I won't know until I get to the end of that row which one of those is the shortest, which is why my worst case is looking through all of them, and my best case is also looking through all of them, and the average case shows up somewhere there in the middle. So big O of V there for that one. How about the adjacency list? I think you can pull this one off a little bit better yourselves now. Worst case, best case, average case. Best case is always pretty easy here with the adjacency list. Best case, it's empty or there's just one thing there. I can find that out in constant time. The average case is going to be me looking through all those connections, and the worst case is everybody's connected to this starting point. So same as the previous question. New question. Determine if any flight departs from the airport. It seems silly to have an airport with no flights leaving. It could happen though. So now to see if there's anything that departs from the airport X, how am I going to do this? I've got to look through a row till I find something and I can stop right away. Here I just have to see if it's empty or not. So this one gets pretty easy. Worst case, I've got to check through the entire row to see if there's one connection there. Best case, I find one right away. On average though, I've got to look through half the list to find out that I found something, or the whole list to see that I don't. So big O of V there on the average case. Adjacency list, Look at that, constant time all the way across the board. Worst case is to see if anything departs there. Worst case is if that thing's a null, there's no worst case. If it's a null, I'm not connected to anything. If it's not null, then I'm connected to something, and that's worst, best, and average error, constant time. All right, last one here. Now we're going to associate a distance with each edge. So this is now a weighted graph. We already had that. But we're going to add a cost as well. So we've got a cost and a distance, and you can see that here, this JFK to ORD, now 740 miles at $200. So what's an algorithm that's going to determine the greatest distance for the least cost that I can fly from JFK? I'm just trying to rack up frequent flyer miles. So what I'm trying to see is like, what's the greatest distance for the least amount of cost that I can spend here? And what's the complexity of that? The hint in the question there is a ratio. So obviously we're gonna have to do some division there. So we do some division to find out the miles per dollar spent, and just figure that out. Looks like ORD is the winner there, right? If I divide that, 740 divided by 200, it's over 3.5 miles per dollar there in Miami. It's not quite 2 miles per dollar. In Boston, it's much less than that. So the way that I would pull this off is just do that division, and then similar to the find the maximum distance, here I'm just trying to find the maximum ratio or the minimum distance or minimum ratio. So all I would have to do is calculate that and then look at each one of the things in there. So my complexity then would be a big O of 1 plus E over B. All right, let's get into some route planning. Now we're getting a little bit deeper into these algorithms. Determine the most efficient route. That means the lowest cost or the lowest trip distance flown from X to Y on any trip, non-stop or connecting. So now we can say I could travel from San Francisco to Boston directly, or I can travel from San Francisco to Chicago to Boston. I want to know which one is cheaper. All right. That question I was just asking, sorry, the most efficient route from any X to any Y on a nonstop or connecting flight is what's known as single source shortest path. We're trying to find the shortest path to get to any vertex from some starting point. There's a few ways that we can do this. We might start with a depth first search, much like we did in Project 1. Turns out that for finding a single source shortest path, depth first search will not work for us. And we saw that in Project 1. You kind of get going off on a trail and you travel off. So depth first search is only going to give me this shortest path when I'm working in a tree. May find the wrong answer because there's multiple paths in graphs. If you think of this position and this neighbor right next to it, if I start traveling this way and work through some connections and come back around here, I can find the connectivity that I might have found a different way if I had been going breadth first. Breadth first search, remember, we're going to look at all of the locations that's 1 spot away, and then I make my circle a little bigger. All the places that are 2 spots away, I make my circle a little bigger. All the places that are 3 spots away, 4 spots away, 5 spots away. So a breadth first search keeps expanding the radius of how far away you search from the home base. And so that's what a breadth first search does. However, a breadth first search is not going to be able to find me the single source shortest path if I've got weights. Because the breadth first search is going to say, can I get there in 1 step? Or can I get there in 2 steps? Can I get there in 3 steps? Doesn't matter how long those steps are. What a breadth first search can't find is, well, I can get there in 2 steps, but if I work really hard and take 4 hops, I can actually get there cheaper. Breadth first search won't find that because it stops after the 2 steps and finds a connection and then says, we've found it. So if we're working with unweighted edges, breadth first search will give us a shortest path, but that's only in an unweighted graph. And most of the time when we're trying to find shortest, we're using weights. So the way that we can do this is with Dijkstra's algorithm. And we won't talk about Dijkstra's today, we'll talk about it the next time around. But Dijkstra's algorithm does work for the single source shortest path when I've got weighted edges. So let's take a look at how depth first versus breadth first works. So that typo, pay no attention to the breadth up at the top there. That should be breadth. So in a breadth first search, you can see here in these two tree representations. So these are trees, and you can see how in a depth first search we get all the way down to the bottom before we start moving across. That's why we call it depth first, right? A goes on to B, goes on to D, goes on to H. Now we've hit a leaf node and we can work our way back up and across. So that's depth first search. In a breadth first search, you see that we start at the top and work our way across, right? So first we do A, then we do B and C at the next level, because those are both one step away from A. Then we do D, E, F, and G. Those are all 2 steps away from A. Then we do H, I, J, and K. Those are all 3 steps away from A, and so on. So that's how depth first versus breadth first looks in trees. How about when we look at them in graphs? So if I've got some graph G and I'm exploring the edges from G to C, if any path exists. Remember, we said that a depth first search won't find you a shortest path in a graph. But you can use a depth first search to see if any path exists. And sometimes that's good enough. The way that we use the depth first search is with a stack. So stack mode on project 1 was doing a depth first search. Algorithm works great on graphs and digraphs. It can discover a shortest path, but it certainly is not guaranteed to be the shortest path. And we definitely saw that on P1. Path discovered may be a shortest path, but it's not guaranteed. So here's what a depth first search might look like here. Here's me going from, I think, where am I going here? SFO to JFK. I think that's the goal. And I've got this stack, and you'll see I'll put some stuff in there. So I'll start out with SFO, and I'm just like I did in project 1, I'm going to seed the container. I'm going to put that starting location in there, and then I'm just going to keep removing things from the stack and marking them as discovered. You see the little circle around SFO. It's marked as discovered now, so I won't discover that again. Right from there, what I'm going to do is work my way sort of clockwise around, just for visual purposes. So as I look at the edges that come off of here, I'm going to take that top edge, that 2704 to Boston, then I'll take the 1846 to Chicago, I'll take the 1464 to Dallas, and I'll take the 337 to LAX. I'm going to push all of those things into my stack. As I push them into the stack, you'll note that I mark them as discovered so that I won't try to discover them again. But now I'm done with investigating connections from SFO. So what do? I can pop something from LAX, or pop something from the stack that's LAX. I'll bring that over here, and now I'll investigate around LAX. If I look north from LAX and draw this imaginary line and then circle my way around clockwise, I'll see that I come across Dallas, which has already been discovered, so I don't put that into the container. Then I hit Miami, that hasn't been discovered, so I'll put that in the container. And then I'll come back around and see that SFO has already been discovered, so I don't put that in the container. So all I end up doing is pushing Miami on there. Now Miami is marked as been discovered. This is me doing depth first search, just like we did it in project 1. As I pull the next thing from the top of my stack, Miami comes over here, pop that off, put that in my list of things to look at. I'm going to look straight north from there and see the first thing that I hit as I start from straight north and move around clockwise, I'll hit JFK. And JFK being what I was looking for, I'm going to go ahead and say there's my goal. I'm going to bring this down here, and then this path that I discover looks like my depth first search has found me the path that goes from San Francisco to LAX to Miami to JFK. That found it. Total distance there, 3,769. We can probably get there cheaper than that if you were to do this yourself, how would you do it? What's the correct answer? If I'm trying to get from San Francisco to JFK, and you do a quick peek in there, I think cutting across the middle of the country is probably the fastest way to do it. SFO to Chicago, that's for 1846, plus Chicago to JFK, that's another 740. So it looks like I can get there in 2586. So that's my optimal. Depth first search did not find my optimal. It found that a path exists, but it did not find a shortest path. Here's project 1, written for you in pseudocode. Mark the source as visited, push the source to a stack. That's me seeding the container. Then as long as the stack isn't empty, keep taking candidates out and investigate everything around that candidate. If I find the candidate, win. All right, that's depth first search, that's P1. How this looks in another illustration here, you see I'm trying to get from A to E using depth first search. How do I do this? I put the things adjacent to A into my stack. That's B, C, and D, right? Then I'll tack on B, C, and D just like that. So there's my stack. Now if I pull off of the stack, I'll pull D off of there. D has what we call back edges because D's edges are connected to things that are already discovered. So I don't get anything new based on D. As I pop C, I've got a back edge to A and D, but I've got a new discovery edge to get me to E, and this is how I find my path from A to E with depth first search. If I analyze the complexity of this, we remember that depth first search gets called for each vertex at most once. I'm looking at that thing. I've only discovered each vertex at most once because I mark it as discovered and then I never can discover it again. If I've got an adjacency list for each of my vertices, then each one of those things is visited at most once. And the set of edges that gets distributed over there looks like, on average, E over V of them. So my DFS is 1 plus E over V to see each one of those vertices. To see all of the vertices, I multiply that by V, and I say that analysis of DFS looks like a big O of V plus E when I'm doing the number, the number of vertices and edges when I'm doing the DFS with adjacency list. If I go to adjacency matrix, same thing, I'm only calling it once for each one of my vertices, but now each one of my vertices has a row of size V that I have to look at. So I gotta look at each one of those V items, and so I end up with this big O of V squared. It's quadratic in the number of vertices to do a DFS in an adjacency matrix. So, slight difference there. Adjacency list is a big O of V plus E. Now we're taking vertices and edges, whereas in DFS with the adjacency matrix, it's just the big O of V squared. So it has no concern about the number of edges, just the number of vertices. How about breadth first search? Very similar to the depth first search. The only thing that changes, Q, not stack. We're gonna do the same thing. It will discover a shortest path for me if I'm talking about total number of trips though, right? So it says here, discover the shortest path only on unweighted graphs or where all edges have the same weight. So here's a similar animation of the previous one. Now I've got a Q with my front at the bottom there. It's a little bit easier on a slide to go vertical than it is horizontal. So my Q with the front at the bottom, and I'm going to do the same trip from San Francisco to JFK. Right, I'll put SFO in the container, mark it as being discovered, get things started, jump into my loop. Now I'll discover clockwise from SFO. As I pull that off of there, this is my current position, and I find Boston, I find O'Hare, I find Dallas, I find LAX. So that's me going north and then working my way around clockwise to discover everything that's adjacent to San Francisco. Since I'm using a Q now, I'm going to start from the front. That's now Boston, not LAX, right? So we'll pull Boston over here, and then we'll examine from Boston. Same thing, I'm going to start out north, travel around clockwise. So the first thing I hit is Miami, and then I hit JFK. say, well, hey, JFK was where I was trying to go. So let's stop this search. Even though there's other things in the queue in front of me, I was trying to get to JFK, so I end up by adding that distance there. And it looks like we got some slide niftiness, right? I gotta fix that one. SFO starts there, goes to Boston in 2704, goes to JFK in another 187. Total distance there, 2891. So now I know that my shortest trip, we already checked that one out. We said that was 2586, and it was a 2-hop from San Francisco to New York, or sorry, San Francisco to Chicago to New York. So I found a different 2-hop. So in that respect, depth first search has founded me the shortest number of trips path. That's another way that I can get to JFK in 2, right? It goes San Francisco all the way across to Boston and then back to JFK. So that's another way that I can get there in 2 hops. The only other way that I can get there in 2. But it's not the shortest. It's still longer than I need it to be. This is what it looks like. All we've changed from the previous pseudocode is queue and front and back and top and stack. Here's what it looks like as I try to do this. Again here, I'm going to be sticking these things in my queue, and my queue is this dashed line thing. So I'll start out at A, and the first thing I put in there is B, then I add C to the queue, and I put D in the queue. So now as I continue to try to discover from there, I'm going to say, let's go from B. B has back edges to A and C, because A and C have already been discovered. And it has a forward edge, a discovery edge to E, so I'll stick that into the back of my queue. So it's kind of interesting to look at here, but it goes from C to D to E, right? In this case, I'm trying to go from A to F, the last item in my graph. So the next up is I take C, because that's next in the queue. It's got back edges to A, B, D, and E, but it does have a discovery edge to F, and that gets me from A to F. So this is how Project 1 worked. We don't have to dwell on that. Let's analyze it. In BFS, we haven't changed much. Only the container that drives this, not the representation, not the number of edges, nothing really. So we don't find it surprising that there's no real distinction here between the BFS complexity and the DFX complexity. So the BFS complexity for adjacency list is 1 over E plus V for each individual vertex, and since there's V of them, I can multiply that out and I get a big O of V plus E. So the BFS analysis of an adjacency list application is linear in the number of vertices and edges, big O of V plus E. Same with the adjacency matrix here. Now I've got the entire row to deal with, so it's V rows, V items per row, ends up being quadratic, big O of V squared, total number of vertices to do a breadth first search with an adjacency matrix. All right, let's peek at Dijkstra's algorithm. I think we're going to do this one today. Right? I said we weren't going to do it till Thursday. We're doing it today. So Dijkstra's algorithm is going to take this weighted graph that we're so familiar with now, and now I'm going to use this to discover a shortest path. So that one that I did with the human eyes to go from SFO to Chicago to New York, I'm going to use Dijkstra's algorithm to calculate that one properly, right? And so I can find the shortest path from some source S to a goal G. We will see that one, and we will love it. So, yeah, I keep going back and forth. Dijkstra's algorithm is upcoming. I was right. So here's my summary here. I've got a bunch of background and definitions. We talked about weighted, unweighted, simple, talked about directed, undirected, talked about sparse, dense. We talked about implementation methods, adjacency matrix, adjacency list. We looked at a couple of different ways that we might be able to do some graph searching. Depth first search, and we saw that that would get us connectivity if it existed. Wouldn't necessarily find us the shortest path, but it would find if any path existed. A breadth first search would find us a shortest in number of hops path, but not necessarily a shortest in distance path if it was possible to have a shorter path that had more hops involved. Breadth first search wouldn't find that. So breadth first search is only finding an optimal answer if I've got an unweighted graph there. And lastly, we introduced Dijkstra's algorithm, which will be optimal for my weighted graphs, as long as I don't have negative values in there. As long as my edges don't have any negative weight edges, as long as my edges are all the same sign, Dijkstra's algorithm will work for me. But we are going to talk about that one on Tuesday. So that gives it, the rest of us, that does it for our graph introduction here. We'll talk about the MST algorithm and some more algorithms in graphs on Thursday. All right, so we'll hang out here and chat for a few and see what we can come up with. All right? So it looks like we got nobody here on my side with me. So I had no wingman answering my chat questions. So I can cruise back here and see if I can pull this off. We talked early question from Shiv here about, do parallel paths have to be paths directly from A to B, or can a path from A to C to B be parallel? No, a parallel path is definitely two connections, two or more connections between the same two nodes, two or more direct connections. Yep. I was JFK at Washington, D.C. I don't know. I didn't draw the graph. I don't even know who did. Snagged it. So yeah, we definitely have the fact that a complete graph is a dense graph, because in that case, complete graph, we've got every vertex connected to v minus one other vertices, and the total number of edges then ends up being v squared minus v over 2. And so we do have the big old v squared. So I guess then all complete graphs are dense, just not all dense graphs are complete. Yeah, the diagonal is always 0 in the distance matrix. It'd be 0 or infinity. Infinity is better in the distance matrix, remember, because you would say, is there a connection? Because then using infinity makes it so that you don't have to check whether there's connectivity. You just try to maximize, you try to minimize with it. So if I don't want to know whether or not there's connectivity, I can just say, well, this one is an infinity. I just choose not to use that. The fact that it doesn't actually even exist physically, that's immaterial, right? It's just been great for my algorithm to be like, hey, this distance is really large. Let's try to do something else. If I can take one other trip, that's better. So you use infinity, yeah. In terms of when we're talking about infinity, this is a good question. Jae-Hyun talked about it. We use infinity when we're talking about floating point types. So if you are talking about integer types, then int max works just fine. But using max with floating point types is not the way to go there. That's where you use infinity. So that's where, because most, your integral types don't even have they don't have infinities. They only have maxes. So you use infinity when you're talking floating points. I know that all of those pictures on in the slides were all using integer-based weights, but that's the clear up there. Manhattan would be dense. E over V. All right. How do you go back up the tree in DFS? Okay, yeah, so when we do a depth first search in a tree, and we talked about that one in the early lecture this morning, we talked about the distinction between doing a depth first search with a stack and a container versus doing a depth first search and a stack being the call stack. So in a recursive function, you use this call stack as your stack, but there is still a stack that drives it. Whereas in the container version, which is what we saw in project 1, we used the container to go back to our stack. Whereas in those pictures that had the tree-based depth first search, there you can think of that as being a recursive call. We started at A, and then A calls it on B, and B starts as if it's the root of the whole thing and just starts moving itself down that way. So that's why in our depth first search on the tree, we tend to stay on that left-hand side, whereas you might think, well, if I go to A's children B and C, how come C doesn't come out of the stack first? C would come out of the stack first if we were talking container version. But since we're calling call stack version, the B comes out. And the only difference is when I use container version for my stack, I would still get a depth first search. It would just be right heavy, and I would go down the right side before moving my way across to the left. When I use recursive, I go left heavy, and I still go all the way down to the left before I start moving my way up and across to the right. So that's the distinction there as we talk about depth first search and trees and graphs and doing it with a stack container or a call stack. So hopefully that clears that one up. And it is one of our tree traversals. We talked about tree traversals here in the last few previous lectures. So our depth first searches are all those in order, pre-order, post-order traversals. And because those are all different depth first searches, but they all get down to the bottom before they work their way across here. That's what makes them stack based. That's what makes them depth first. Then if we're going level order, that's my depth first search or my breadth first search. Sax lessons on the lecture. I'll do a sax show next time we got a live lecture. Come check me out on the watch parties. We usually start those out with some music, either some lo-fi or some Hamilton instrumentals, whatever I'm feeling that day. Okay, so Floyd-Warshall algorithm is a graph search algorithm. The Floyd-Warshall algorithm can be used to solve the, let me say this right, single source, many destination, right? Single source shortest path, that's Dijkstra's, but you can think of if I want to get the shortest path from any location in the graph to any other location in the graph, you can figure that out with the Floyd-Warshall algorithm. Floyd-Warshall actually ends up being a DP algorithm, dynamic programming algorithm, that could also be done by performing Dijkstra's algorithm V times. They both end up being the same complexity, but we'll actually touch on Floyd's in the next lecture. Right as we end it, we sort of like peek at the slides where Floyd-Warshall used to be. We don't use it anymore in this course, but they're perfectly good slides, so they still exist. If you check out your PDF, you should find them there if you want to look into it. It's a fun algorithm to watch. I really like the way the guy at the open source, the open course where at MIT, he does a really good description of how Floyd-Warshall works. All right, that puts us past our time here. I think we're about good. We'll be doing office hours here, starting up short order here for the profs, and then we'll go at it. So Thanks for coming. We'll see you on Thursday. We'll be doing watch parties 10 to 12, and then regular lecture 12 to 1:30. Have a good one.